Look up at the night sky, and you might see countless twinkling stars, serene and silent. But beneath that calm surface, a cosmic forge is at work, a process so powerful it creates the very atoms in your body. The iron in your blood, the carbon in your cells, the calcium in your bones, all were born in the heart of stars, billions of years before Earth existed. How do stars perform this alchemy? How do they take the simplest element, hydrogen, and transform it into the complex building blocks of life, the metals that shape planets, and even the gold we treasure? Tonight, we'll journey into the fiery hearts of these stellar furnaces, following the stages of fusion, the explosive deaths of massive stars, and the cosmic recycling that spreads these elements across the universe. From the gentle glow of our sun to the cataclysmic brilliance of supernovae, every star has a story to tell. By understanding how stars forge the elements, we begin to see the universe not as distant and indifferent, but as intimately connected to us. Everything we are, everything we touch, was once part of a star. Prepare to drift into a universe of light, fire, and creation, and discover the extraordinary journey of matter itself. Birth of a star. In the quiet depths of the cosmos, where space stretches endlessly and darkness seems absolute, the story of creation begins in the most unassuming way. A cloud of gas, composed mostly of hydrogen with traces of helium and dust, drifts silently through the void. These clouds, known as nebulae, appear as faint smudges against the star-strewn night sky, their presence almost ethereal, like the whispers of a secret the universe has not yet revealed. But within these clouds lies the raw material for some of the universe's most magnificent creations. Stars. Gravity, that invisible hand that shapes worlds and governs the motion of galaxies, begins to act on the nebula. Small fluctuations in density, imperceptible to the eye, grow over eons. Pockets of gas collapse under their own weight, the cloud contracting slowly yet inexorably. As matter gathers, it pulls in more matter, the process accelerating. The cloud fragments into clumps, each a potential star, each a seed of light waiting to ignite. This is the quiet birth of a star, a process both slow and inexorable, occurring over millions of years, yet crucial for the creation of all elements that will follow. Within the densest cores of these fragments, temperature and pressure rise dramatically. Heat builds as atoms collide with ever-increasing intensity until conditions are extreme enough for the first nuclear reactions to occur. Here, in these hidden, invisible furnaces, hydrogen nuclei fuse to form helium, releasing tremendous amounts of energy. This energy is what we perceive as light and warmth when the star finally emerges from its cocoon of gas and dust. For a newborn star, this moment is its awakening, the transition from a collapsing mass of gas into a self-sustaining fusion engine. The onset of fusion is delicate. The inward pull of gravity constantly threatens to compress the star further, while the outward pressure from nuclear reactions works to balance it. When these forces find equilibrium, the star achieves a stable state called the main sequence, a phase that can last millions to billions of years, depending on the star's mass. During this time, the star quietly converts hydrogen into helium in its core, a process that powers its light and sustains its presence in the cosmos. This is the star's heartbeat, the rhythmic pulse that defines its life. Not all stars are created equal. Smaller stars, like our sun, burn steadily and live for billions of years, their fusion gentle but persistent. Massive stars, many times the sun's size, burn far hotter and faster, consuming their hydrogen fuel in mere millions of years. These giants shine with breathtaking brilliance, lighting up their surroundings and influencing the formation of nearby stars and planets. Yet, regardless of size, all stars are factories of matter, converting simple hydrogen into the building blocks of the universe. It is in this crucible that the journey of elements begins. Hydrogen, the simplest and most abundant element in the universe, is fused into helium. This helium, while inert by comparison, is not the end, but a stepping stone. In stars more massive than the Sun, once hydrogen is depleted in the core, the star contracts under gravity until temperatures become sufficient for helium fusion. Helium nuclei combine in a delicate dance, producing carbon and oxygen, elements that are the very foundation of life. The star, in essence, becomes an alchemist, transforming the raw materials of the universe into the atoms that will one day form planets, oceans, and living beings. The birth of a star is also a story of motion. Surrounding the young star is a disk of gas and dust, remnants of the original nebula spinning gently. Within this protoplanetary disk, clumps of matter collide and stick together, gradually forming planets, asteroids, and comets. The star's light and stellar winds begin to sculpt these newborn worlds, clearing paths in the surrounding material and setting the stage for complex planetary systems. The birth of a star, then, is inseparable from the creation of the worlds that orbit it. Yet, even as the star settles into its main sequence phase, it is not entirely quiet. Magnetic fields twist and coil within its interior, occasionally erupting to the surface in spectacular flares. Convection currents stir the plasma in the outer layers, creating sunspots and storms of unimaginable scale. The star is alive, dynamic, and constantly interacting with its environment, shaping the space around it even as it produces the elements at its core. For massive stars, the journey from birth to death is rapid and dramatic. As hydrogen runs out, the core contracts and heats until helium begins fusing into heavier elements. The star may develop layers like an onion, each shell fusing progressively heavier elements in a delicate balance of gravity and nuclear pressure. Carbon, oxygen, neon, magnesium, silicon, and eventually iron are created in these shells, the star building a complex internal structure that mirrors the cosmos itself. This is stellar alchemy at its most advanced, a process hidden from view, occurring in the hearts of giants, forging the elements essential for planets and life. The death of these massive stars is as dramatic as their birth is quiet. When fusion can no longer sustain the pressure needed to counteract gravity, the core collapses. The outer layers are expelled in a supernova explosion, scattering the elements forged in the star across interstellar space. Gold, uranium, and all the elements heavier than iron are born in these cataclysmic events, seeding the universe with the material necessary for new stars, planets, and eventually, life. Even the Sun, destined to become a red giant in billions of years, will contribute carbon, nitrogen, and oxygen to the cosmic mix when it sheds its outer layers in a gentle planetary nebula. Through this cycle, stars are both creators and destroyers, recycling matter over billions of years. Their births, lives, and deaths forge a universe rich in chemical diversity. Every atom in our bodies, every molecule of water, every speck of dust on Earth, carries the legacy of stellar forges. In understanding the birth of stars, we understand the origin of the elements, and in doing so, our own place in the cosmos. And so, when we look at the night sky, the faint glow of distant stars is not just light traveling across space. It is the heartbeat of cosmic creation, a signal from the furnaces that forge the building blocks of everything we know. Each star tells a story of collapse and ignition, of fusion and transformation, of quiet patience and explosive brilliance. It reminds us that the universe is not static or indifferent, but alive in the slow, powerful process of creation, a process in which we, too, are participants, made of the very matter these stars have labored to produce. The birth of a star is not merely the beginning of a life cycle. It is the opening act in a grand cosmic drama, one in which elements are forged, worlds are shaped, and the seeds of life are sown. And as we drift away from this thought, imagining the quiet collapse of a nebula, the gentle ignition of fusion in a newborn star, and the slow unfolding of chemical creation, we glimpse the profound truth. Everything around us, everything inside us, originates in the stars. Hydrogen burning, the sun's heartbeat. At the heart of every star lies a fire that never fades, a furnace where the simplest element, hydrogen, is transformed into helium in a process of unimaginable power. This process, known as hydrogen burning, is the foundation of a star's life. It is here, in the dense core, that the star begins its long career as a cosmic alchemist, forging energy from matter and producing the elements that will one day seed planets, atmospheres, and life itself. Imagine stepping inside the core of a star. It is a place of extremes beyond human experience. Temperatures of millions of degrees, pressures crushing like 1 trillion tons, pressing on every square centimeter. A plasma so dense that atoms are stripped of their electrons. In this cauldron, hydrogen nuclei, protons, move at astonishing speeds. They collide and under the immense pressure and temperature, fuse together. When two protons merge, they form deuterium, releasing a positron, a neutrino, and a burst of energy in the form of gamma rays. These gamma rays take thousands of years to escape the core, bouncing from particle to particle, gradually making their way outward to the star's surface, where they emerge as the sunlight that warms planets and illuminates the universe. This fusion process is extraordinarily efficient. The amount of matter converted to energy is tiny, almost imperceptible, yet the energy produced is vast. For every second, our sun converts millions of tons of hydrogen into helium, radiating energy across the solar system. This energy provides the pressure needed to counteract the inward pull of gravity, keeping the star stable. The balance is delicate, a cosmic dance between collapse and expansion, yet it can last billions of years. Hydrogen burning is not the same in all stars. In smaller stars like our Sun, it occurs primarily through the proton-proton chain reaction, a stepwise process in which protons combine in stages to eventually form helium. In more massive stars, the CNO cycle dominates, using carbon, nitrogen, and oxygen as catalysts to speed up the fusion process. Regardless of the method, the result is the same. Hydrogen is fused into helium, and energy is released, keeping the star alive and luminous. The star's heartbeat is steady and relentless. Each fusion reaction contributes to a vast, intricate network of energy transfer. Photons bounce, scatter, and collide, slowly diffusing outward through the radiative zone. They take thousands of years to escape, gradually feeding the outer layers of the star, where convection currents stir the plasma. Hot material rises, cools, and sinks, circulating heat and maintaining the star's equilibrium. This rhythmic motion, the steady fusion of hydrogen, and the turbulent convective flows combine to create a star that is alive in every sense. Dynamic, balanced, and radiant. Hydrogen burning is also responsible for the synthesis of helium. While helium may seem simple compared to heavier elements like carbon or oxygen, it is a crucial building block. Helium nuclei, or alpha particles, will later serve as fuel for subsequent stages of fusion in more massive stars. Without hydrogen burning, stars would never progress to the creation of heavier elements. It is the first step in a long chain of cosmic alchemy, setting the stage for the diversity of matter we observe in the universe. Beyond the core, the energy produced by hydrogen burning has profound effects on the star's surroundings. The outward radiation exerts a pressure that shapes the star's atmosphere, drives stellar winds, and influences the formation of nearby planets. Light pressure from young stars can push gas and dust into intricate structures, carving gaps in protoplanetary disks and sculpting nebulae into breathtaking forms. In this way, hydrogen burning does more than sustain the star. It shapes the cosmos around it. The importance of hydrogen burning extends to life itself. Without this process, stars like our Sun would not emit the steady light and heat necessary for habitable planets. The energy produced sustains climates, drives weather systems, and powers photosynthesis. The helium produced, along with later fusion products, contributes to the chemical richness that eventually forms the building blocks of life. Every breath we take, every movement we make, is ultimately linked to the steady fusion of hydrogen in the hearts of stars billions of years ago. For massive stars, hydrogen burning is only the beginning of a more dramatic life story. Their higher masses mean greater gravitational pressure in the core, higher temperatures, and faster fusion rates. These stars burn hydrogen so rapidly that their main sequence lifetimes may be only a few million years, a fleeting blink in cosmic time. Yet in that brief period, they produce enormous amounts of energy and set the stage for the creation of heavier elements in later fusion stages. Their brilliance outshines entire clusters of smaller stars, and their influence shapes the galaxies around them. Even as hydrogen burning proceeds, the star is subtly preparing for its next act. As helium accumulates in the core, the balance of pressure and gravity begins to shift. The star's interior temperature slowly rises, and eventually, conditions will be right for helium burning. This transition is a quiet but profound signal that the star is maturing, moving along the path that leads to carbon, oxygen, and eventually the heavier elements that form planets, metals, and life. Hydrogen burning, then, is both a sustaining process and the opening act of a grand alchemical play. The process of hydrogen burning is mirrored in stars across the universe. Nebulae everywhere produce new stars, which ignite and begin their lives fusing hydrogen into helium. Over billions of years, this process has transformed the cosmos, building a layered chemical structure from the simplest element to the complex palette that forms planets, atmospheres, oceans, and living creatures. Every star, from the smallest red dwarf to the largest blue giant, participates in this cosmic alchemy, linking all matter in a web of creation that stretches across space and time. And so, when we look up at the sun or the stars in the night sky, we are witnessing the work of hydrogen burning, a slow, steady, life-sustaining fusion that has been occurring for billions of years. Each photon that reaches us carries with it the signature of this process, a reminder that our lives are connected to stars in ways both intimate and profound. The very atoms in our bodies were once hydrogen nuclei, forged in the hearts of stars, fused into helium, and eventually scattered across the cosmos in a cycle of creation and transformation. Hydrogen burning is more than a nuclear reaction. It is the heartbeat of the cosmos. It sets the rhythm for the life cycles of stars, the formation of planets, and the creation of the elements that make life possible. It is the first chapter in a story that continues through helium burning, advanced fusion, supernova explosions, and cosmic recycling. A story that spans billions of years and connects us directly to the universe. In contemplating hydrogen burning, we understand both the fragility and the power of stars. They are engines of creation, but they are also finite. Even the sun will one day exhaust its hydrogen, transitioning into helium fusion and beyond. Yet while it burns, it sustains everything in its orbit, sending light, warmth, and the raw materials of life across the solar system. Hydrogen burning, quiet and persistent, is the gentle rhythm that underpins cosmic evolution and human existence alike. Helium fusion. Carbon and oxygen are born. As stars age, their life cycles enter a new and extraordinary phase. The steady fusion of hydrogen into helium, which sustained the star for millions or even billions of years, begins to wane as the core's hydrogen supply diminishes. Gravity, relentless and unyielding, starts to reclaim its dominance, compressing the core further, raising temperatures and pressures to extremes beyond what hydrogen fusion could ever achieve. It is in this crucible of heat and gravity that helium fusion begins, a process that marks the star's transition from a simple hydrogen furnace to a more complex alchemical engine. Helium fusion is both delicate and extraordinary. Unlike hydrogen fusion, which involves combining protons, helium nuclei are already heavier, composed of 2 protons and 2 neutrons. Fusing these alpha particles into larger nuclei requires even more extreme conditions, temperatures of hundreds of millions of degrees, and pressures far surpassing anything in the previous phase of the star's life. In stars more massive than our Sun, the core temperature eventually rises high enough for the triple alpha process to occur. In this reaction, 3 helium nuclei combine in a precise sequence to form carbon, releasing energy in the process. The creation of carbon is profound. Carbon is not just another element, it is the foundation of life as we know it. Its ability to form complex chains and structures makes it the scaffolding for organic molecules, for proteins, for the very cells that will one day exist on planets born from stardust. Every atom of carbon in our bodies owes its origin to this stellar process, hidden within the cores of stars, far from the reach of human observation. Yet without it, the universe would be sterile, barren, and unimaginably simple. Helium fusion does not stop at carbon. In stars with sufficient mass, the carbon produced can further fuse with additional helium nuclei to form oxygen, a second critical building block for life and for planetary systems. The sequence of reactions is intricate and highly dependent on the temperature, density, and mass of the star. Helium nuclei collide at extraordinary velocities, overcoming their mutual electrostatic repulsion, merging into carbon-12, and then, in subsequent collisions, forming oxygen-16. This delicate dance of nuclei is responsible for generating much of the oxygen found throughout the cosmos, which will later combine with hydrogen to form water, an essential ingredient for life. The star's core, now a dynamic laboratory of helium fusion, is surrounded by layers of hydrogen still burning in a shell outside the core. This layered structure ensures the star remains stable, even as its internal composition becomes increasingly complex. The energy generated by helium fusion supports the star against gravitational collapse, prolonging its life while creating elements critical for the chemistry of future worlds. Each layer in the star acts as a furnace, producing elements that will one day be ejected into space, scattered across the galaxy, and incorporated into new generations of stars and planets. The balance within the star is delicate. Helium fusion occurs at temperatures far higher than hydrogen fusion, and the reactions are highly sensitive to changes in temperature and density. If the core becomes too hot or dense, fusion accelerates dramatically, producing energy at an uncontrollable rate. In stars significantly larger than the Sun, this can lead to pulsations, contractions, and expansions that dramatically reshape the star's structure. These pulses are not destructive, but instead act as natural regulators, allowing the star to slowly stabilize while continuing to fuse helium into carbon and oxygen. The products of helium fusion are not confined to the core. Stellar winds and convection currents transport some of the newly formed carbon and oxygen toward the outer layers of the star. Over time, these elements may be released into space when the star reaches the end of its life. For medium-sized stars like the Sun, this occurs gently as the star sheds its outer layers to form a planetary nebula, leaving behind a white dwarf enriched with carbon and oxygen. For massive stars, the release is far more dramatic, as supernova explosions scatter the newly forged elements across interstellar space. These processes have profound implications for the chemical evolution of galaxies. Carbon and oxygen, once formed in the cores of stars, are returned to the interstellar medium, enriching the gas clouds from which new stars and planets will form. Each generation of stars builds upon the ashes of the previous one, creating a cosmic cycle of birth, fusion, and dispersal. Over billions of years, this cycle leads to the diversity of elements observed throughout the universe, from the iron in planets to the carbon that forms the backbone of life. Helium fusion also serves as a prelude to the star's eventual fate. In stars significantly larger than the Sun, once helium is depleted in the core, contraction and heating will continue, igniting fusion of progressively heavier elements. Carbon can fuse into neon and magnesium, oxygen into silicon, and eventually the star builds an onion-like layered structure with increasingly heavier nuclei toward the center. This sequence sets the stage for the dramatic and violent supernova explosions that will forge the heaviest elements and scatter them across the cosmos. From a human perspective, the significance of helium fusion is staggering. The oxygen we breathe, the carbon that forms our cells, the calcium in our bones, all trace their origins to helium fusion in stars that lived and died long before our solar system formed. Each breath of air, each molecule of water, each organic molecule is a testament to the star's alchemical power. We are, quite literally, made of star stuff, connected to processes that began billions of years ago in the hearts of distant suns. The energy released during helium fusion is immense, rivaling that of hydrogen burning despite involving far fewer nuclei. This energy maintains the star's radiance, prolongs its life, and ensures the stability of its surrounding planetary system. Without helium fusion, stars would be unable to generate the heavier elements necessary for the formation of planets capable of supporting life. The process is both a continuation of the star's life and a gift to the universe, producing the raw materials for the next generation of cosmic creations. The transition from hydrogen to helium fusion also transforms the star's internal dynamics. Convection becomes more pronounced in regions where the energy transport is insufficient to carry the flux outward via radiation alone. These convective zones mix material, distribute newly formed elements, and create cycles of motion that maintain the star's stability. From the outside, these processes are invisible, yet they are critical to the star's ability to continue producing elements over millions or billions of years. In massive stars, helium fusion ignites with explosive brilliance. The energy generated can temporarily exceed the star's normal output by orders of magnitude, causing the outer layers to expand and contract in waves. These pulsations can shed material, enriching surrounding space with carbon and oxygen even before the star reaches the end of its life. Thus, helium fusion begins the process of dispersing life's building blocks into the cosmos long before the ultimate supernova occurs. In summary, helium fusion is a pivotal phase in stellar evolution. It transforms stars from simple hydrogen burners into chemical factories capable of producing the elements essential for life. Carbon and oxygen, born in these fiery hearts, will one day become part of planets, oceans, and living organisms. The star itself remains a dynamic, living entity, balancing gravity, nuclear reactions, and convection to sustain this delicate, ongoing alchemy. Through helium fusion, stars begin the long and intricate process of creating the universe's chemical diversity, connecting us, in ways both subtle and profound, to the life cycles of suns that lived billions of years ago. The onion of a star, advanced fusion. As a massive star matures, the cosmic dance that began with hydrogen and progressed through helium continues with ever greater complexity. The star, now heavy and luminous, transforms into a layered structure, an intricate onion of fusion, where each shell burns a different fuel under conditions far more extreme than before. Inside these layers, nuclear reactions progress toward the creation of heavier and heavier elements, building the chemical foundation for planets, asteroids, and, ultimately, life itself. The core, enriched with helium, contracts under gravity as hydrogen in the surrounding shell continues to burn. The rising pressure and temperature eventually ignite carbon fusion, producing neon, magnesium, and sodium. Surrounding this core, a layer of helium continues to fuse, while an outer shell converts hydrogen to helium. In even more massive stars, oxygen, silicon, and sulfur fusion follow in concentric shells, each layer more exotic, denser, and hotter than the last. These shells are delicate but resilient, with each reaction providing just enough energy to counteract the relentless pull of gravity. To envision this, picture a giant onion in space. The innermost layers are scorching cores where the heaviest fusion occurs. Moving outward, each successive shell burns a lighter element, forming a stratified structure, like a set of nested furnaces. The core is the hottest, the outer layers cooler, yet still extraordinarily hot compared to anything experienced on Earth. Within these layers, atoms collide at velocities beyond imagination, nuclei fuse, energy radiates outward, and matter is constantly transformed. The star is a dynamic system, alive with motion, energy, and chemical creation. Fusion in these advanced stages is far more complex than the hydrogen and helium burning that preceded it. Carbon fusion produces neon, magnesium, and sodium through reactions that require core temperatures exceeding hundreds of millions of degrees. Oxygen burning follows, producing silicon, phosphorus, and sulfur at temperatures approaching 1 billion degrees. Silicon burning produces iron, cobalt, and nickel, the heaviest elements that can be synthesized before energy input becomes insufficient to sustain fusion. This sequence, cascade of reactions, demonstrates the extraordinary capabilities of massive stars to produce the building blocks of the universe. Yet these processes are fleeting. The heavier the element, the more rapidly it is consumed. Carbon may burn for hundreds of years, oxygen for months, and silicon for only days before the star reaches the final stage of iron accumulation. Iron represents a fusion dead end. Unlike lighter elements, fusing iron requires energy input rather than releasing energy. As a result, the core loses the ability to sustain the pressure needed to counteract gravity. The star teeters on the edge of instability, a ticking cosmic time bomb awaiting collapse. The energy produced in these layers does more than sustain the star. It shapes its surrounding environment. Convection currents and radiation pressure transfer heat outward, stirring the plasma, creating turbulence, and redistributing elements within the star. These processes ensure that newly forged nuclei are mixed, ready to be released when the star finally dies. The outer shells, enriched with carbon, oxygen, and other elements, will eventually be expelled, seeding the galaxy with the ingredients for planets, organic molecules, and life itself. Advanced fusion also introduces a profound interplay between gravity and energy. Each layer produces just enough heat and pressure to counteract the crushing pull from above. But as the core grows richer in iron, this balance falters. The outer layers remain buoyant, fusing lighter elements and generating energy, while the iron core, inert and incapable of further fusion, grows ever denser. This imbalance sets the stage for one of the most dramatic events in the universe: a supernova explosion, the final act in the life of a massive star, and the source of elements heavier than iron. Observing this process from afar, we might imagine a star as a serene, luminous beacon. Yet inside, it is a furnace of unimaginable violence and creativity. Nuclear reactions are continuous, intense, and highly energetic. Temperatures reach billions of degrees, pressures soar beyond comprehension, and atomic nuclei collide and fuse, creating elements that will eventually find their way into planets and living organisms. The interior of the star is a laboratory where nature performs experiments on scales, energies, and timescales far beyond human capability. The stratified, onion-like structure also reveals the universality of physics. The same laws that govern hydrogen fusion in the Sun apply in these massive stars, yet under vastly different conditions, they produce entirely new outcomes. The fusion pathways depend on temperature, density, and the star's initial mass, creating a rich diversity of elements. This illustrates how the universe can generate complexity from simplicity, layering one process atop another to produce the variety of matter observed today. Throughout this advanced fusion, the star is also preparing for its eventual death. Each layer is a storehouse of energy and elements, ready to be released in the supernova that will follow. The fusion of heavier elements produces neutrinos, photons, and kinetic energy that begin to push against the gravitational collapse of the core. In the final stages, however, iron accumulation overwhelms the balance. The core can no longer sustain itself, and the star faces a catastrophic implosion that will trigger a supernova, dispersing the layered elements across space and completing the stellar cycle of creation and destruction. Even the smallest details matter. In the oxygen-burning shell, silicon nuclei fuse with alpha particles to form sulfur and argon. In the carbon shell, neon and magnesium form in delicate ratios determined by temperature and density. Each of these reactions contributes to the chemical inventory of the universe, ensuring that when the star finally dies, it releases a palette of elements necessary for planets, atmospheres, and, ultimately, life. The star is not simply burning fuel, it is forging the cosmos, one nuclear reaction at a time. This layered fusion structure also explains the diverse outcomes of massive star deaths. Stars with different masses, rotation rates, and metallicities produce different distributions of elements. Some may create more oxygen, others more silicon or neon. the specific composition of a supernova's remnants depends on the star's internal structure at the moment of collapse, meaning that every supernova is a unique event, producing a distinct chemical fingerprint that will enrich future generations of stars and planets. For humans, the implications are profound. The carbon in our cells, the oxygen we breathe, the calcium in our bones, all were forged in the advanced fusion layers of massive stars. When these stars ended their lives in supernovae, they scattered these elements into the cosmos, mixing with gas and dust to form new stellar systems, including our own solar system. In this sense, the onion-like fusion layers of massive stars are directly responsible for our existence. Every atom in our bodies has a lineage that traces back to these fiery interiors. The onion-like structure also teaches us about the fragility and precision of cosmic processes. Small changes in temperature or density can alter the fusion pathways, affecting which elements are produced and in what abundance. The universe's ability to produce a diversity of elements depends on this delicate balance, illustrating the interplay between chaos and order on a cosmic scale. Stars are not just passive engines. They are finely tuned chemical factories, operating with incredible precision over millions of years. In contemplating the onion-like structure of stars, we begin to see the universe as a vast, interconnected laboratory. Each star is an experiment in nuclear physics, producing energy, elements, and radiation that shape the cosmos. Each layer represents a stage in a long, continuous process that builds the chemical richness of galaxies, ensures the formation of planets, and sets the stage for life. The advanced fusion layers are both a prelude to destruction and a source of creation, a paradox that reflects the dual nature of stars themselves: violent yet life-giving, ephemeral yet enduring. Ultimately, the onion of a star is a testament to the universe's ability to transform simple beginnings into extraordinary complexity. From hydrogen to helium, helium to carbon and oxygen, and carbon to neon, magnesium, and silicon, the star's layered fusion processes build the elements necessary for planets, atmospheres, and life. And when the star dies, these elements are scattered across space, enriching the interstellar medium, seeding the next generation of stars, and continuing the endless cycle of creation. Through this cosmic onion, we see the universe's intricate choreography, a balance of gravity and energy, collapse and fusion, destruction and creation. We begin to understand that every atom, every molecule, and every element on Earth has a heritage traced back to these layered interiors of massive stars. The star, in its quiet grandeur, is a master chemist, crafting the ingredients for the universe's next acts, and ultimately, for life itself. Iron, the limit of fusion. As a massive star reaches the twilight of its life, its once vibrant fusion processes slow to a critical point. The core, now dense with iron, has reached a fundamental limit. Iron cannot release energy through fusion. Unlike lighter elements, which liberate energy when fused, iron demands energy input to combine. The very element that marks stability in atomic structure becomes the star's undoing. It is the ultimate threshold, the invisible wall between life-sustaining fusion and inevitable collapse. For millions of years, the star has fused lighter elements, building layers like an onion, each shell producing heat, pressure, and heavier nuclei. Carbon burns into neon and magnesium, oxygen into silicon and sulfur, and silicon into iron. In each stage, the energy released sustains the outer layers against gravity's relentless pull. Yet now, at the heart of this cosmic furnace, iron accumulates, inert and unyielding. No further fusion can counteract the crushing weight above it. The star teeters on the brink of instability, a ticking time bomb in the vastness of space. The physics of iron fusion, or rather, its impossibility, is rooted in nuclear binding energy. Lighter nuclei release energy as their protons and neutrons combine into more tightly bound configurations. Iron, at the peak of nuclear stability, provides no such advantage. Fusing iron consumes energy instead of producing it, leaving the core bereft of the outward pressure needed to resist gravity. The delicate equilibrium that has sustained the star for millions of years collapses, and the countdown to stellar death begins. As iron builds, the core grows denser and hotter, contracting under gravity. Temperatures soar into billions of degrees, densities become almost unimaginable, and electrons are forced into protons, forming neutrons in a flood of neutrinos. These ghostly particles escape, carrying energy but unable to halt the collapse. In mere seconds, the core compresses from thousands of kilometers to a sphere barely tens of kilometers across, becoming a neutron star. In the case of the most massive stars, collapse continues, forming a black hole where gravity dominates completely, and even light cannot escape. Meanwhile, the outer layers of the star, still burning lighter elements, remain temporarily buoyant. The sudden collapse of the iron core sends shock waves outward, compressing and heating the shells above it. In the most massive stars, this triggers a supernova explosion, a release of energy so vast that it briefly outshines an entire galaxy. It is in this explosive crucible that elements heavier than iron, gold, platinum, uranium, are forged through rapid neutron capture, the R process, and slowly through the S process in the preceding fusion layers. These rare and precious elements, vital to planets and life, are scattered across the cosmos. The iron core is both the end of one process and the prelude to another. Its formation marks the final chapter of nuclear fusion, yet it initiates the universe's next act. Through the collapse and explosion, iron and other elements are ejected into space, enriching the interstellar medium. This matter will seed new stars, new planets, and eventually life. The iron in our blood, the gold in jewelry, and the uranium in planetary cores all trace back to the iron-laden hearts of ancient stars. Even within the core, subtle quantum effects play a decisive role. Electron degeneracy pressure resists collapse temporarily, delaying the inevitable. Yet once the Chandrasekhar limit is exceeded, approximately 1.4 solar masses, degeneracy pressure can no longer hold, and the star succumbs to gravity. The balance that sustained millions of years of fusion fails in an instant, revealing the delicate interplay between quantum mechanics, gravity, and nuclear physics. The iron core illustrates the universality of physics on a cosmic scale. Despite the diversity of stars, the mass, density, and nuclear binding energy converge to produce this predictable outcome: the cessation of fusion and the onset of collapse. Each star that reaches this stage contributes uniquely to the chemical evolution of galaxies, the formation of planetary systems, and the distribution of heavy elements across the universe. The iron within these stars is both a marker of their life cycle and a key to the next generation of cosmic creation. The story of iron is intimately tied to our own existence. The iron in the Earth's core, in the planet's crust, and in our bodies was forged in stars that lived and died billions of years ago. Supernova explosions disperse this iron, mixing it with gas and dust that eventually formed the solar system. In this sense, we are not only observers of the cosmos, but direct beneficiaries of its alchemy. The formation of iron bridges the microscopic scale of atomic nuclei with the grand scale of galactic evolution, connecting stars to planets, stars to life, and stars to humanity. Iron, then, is both a limit and a catalyst. It ends the star's ability to generate energy through fusion while setting the stage for spectacular cosmic events. The collapse of the iron core triggers the supernova that distributes the building blocks of the universe, linking the death of one star to the birth of countless others. It is a reminder that the cosmos operates on cycles of creation and destruction, where endings give rise to beginnings, and the matter forged in one generation of stars continues its journey through the next. The accumulation of iron also explains the diversity of supernova outcomes. Stars with varying masses, rotation speeds, and metallicities produce iron cores of different sizes and structures. These differences affect the intensity, timing, and chemical yields of the resulting explosion. No two supernovae are identical. Each carries the imprint of its progenitor, ensuring that the chemical enrichment of the universe is both varied and dynamic. Finally, the story of iron reminds us of the intimate connection between stars and life. The chemical elements necessary for planets, atmospheres, and biology depend on the life cycles of massive stars. Iron, as the fusion dead end, is pivotal in this chain, marking the transition from a star's life to its contribution to the universe. The universe, through these processes, recycles matter, distributes elements, and builds the conditions for life. Iron is a key node in this eternal chain, linking cosmic evolution to the atoms that compose our bodies. In the end, the iron in stars is more than a physical limit. It is a symbol of transformation, the threshold between a star's steady life and its explosive legacy. It represents the cosmic interplay of forces, gravity, nuclear physics, and quantum mechanics that governs the universe. Through iron, we witness the balance of creation and destruction, the cyclical nature of stellar life, and the profound connection between the heavens and our very existence. Iron is the universe's punctuation mark, the end of a star's energy production, the beginning of cosmic renewal, and the bridge between stellar death and the chemical foundation of life itself. Supernova explosions, forging the heavy elements. The death of a massive star is not quiet. It is a spectacle of cosmic proportions, a cataclysmic release of energy and matter that outshines entire galaxies and reshapes the surrounding cosmos. When fusion reaches its limit at iron, gravity takes control. The iron core can no longer resist collapse, and in a matter of seconds, it implodes. Temperatures soar, densities become extreme, and a flood of neutrinos escapes from the core. The collapse rebounds off the neutron-rich core, or drives instability through the outer layers, triggering the supernova explosion, one of the universe's most powerful and awe-inspiring events. Supernovae are far more than just violent deaths. They are the universe's ultimate forges. In these explosions, conditions become extreme enough for the creation of elements heavier than iron: gold, uranium, platinum, and many others. Nuclear reactions occur at temperatures and pressures far beyond what any stellar core could achieve. Neutrons bombard atomic nuclei in rapid sequences, a process known as the R process, or rapid neutron capture. These neutrons are incorporated into existing nuclei faster than the nuclei can decay, creating exotic and heavy elements that would otherwise never form. At the same time, slower reactions, the S process, or slow neutron capture, occur in stars' advanced fusion layers before the supernova. These processes produce elements such as strontium, barium, and lead, contributing to the chemical richness of the cosmos. The combination of R process and S process nucleosynthesis ensures that almost all elements heavier than iron originate from stars, particularly in massive stars' final moments. Supernovae are, in effect, the universe's master chemists, combining energy, density, and chance to forge the atoms that will seed future worlds. The scale of a supernova is staggering. A single event can release as much energy in a few seconds as the sun will emit over its entire 10 billion year lifetime. Shockwaves propagate outward, compressing, heating, and stirring surrounding interstellar gas. Newly formed heavy elements are blasted into space, carried across light years, enriching molecular clouds that will give birth to new stars and planetary systems. Without supernovae, the universe would lack the diversity of elements needed for planets, oceans, and life itself. Supernovae also illuminate the interstellar medium. The shock waves trigger further star formation, compressing gas and dust in neighboring nebulae. They act as cosmic gardeners, both destroying and stimulating, sculpting the next generation of stellar nurseries. Each explosion is unique, reflecting the progenitor star's mass, rotation, and chemical composition. Some supernovae leave behind neutron stars, others collapse fully into black holes, but all contribute to the chemical evolution of galaxies, ensuring that the matter expelled becomes the foundation for new stars, planets, and ultimately life. Iron, produced in the star's core prior to collapse, plays a critical role in the supernova. The buildup of iron and other heavy elements creates the instability necessary for the collapse to accelerate. The rebound of the collapsing core, combined with neutrino pressure, propels the outer layers outward. In this crucible, extreme temperatures allow for nuclear reactions that produce elements far heavier than iron. Gold, platinum, uranium, and other heavy metals are forged in moments of extraordinary intensity. These are not gradual processes, but instantaneous cosmic alchemy, the universe creating treasures that will endure for billions of years. The light emitted from a supernova is also remarkable. For weeks or months, the explosion can outshine the combined light of all the stars in its host galaxy. This radiation carries not only energy, but information, revealing the chemical composition of the star and the elements synthesized during its lifetime and final moments. Astronomers use spectroscopy to detect these signatures, tracing the creation and dispersal of elements across the universe. Observing supernovae allows us to witness the direct consequences of stellar evolution, to see the universe actively forging the building blocks of life. Supernovae are also responsible for cosmic enrichment on a broader scale. As these elements disperse, they mix into molecular clouds, becoming part of the interstellar medium. Over millions of years, this enriched matter coalesces into new stars, planets, and even life. The calcium in our bones, the iron in our blood, the gold in jewelry, all were produced in these explosions billions of years ago. In this way, supernovae connect us directly to the life cycles of massive stars, linking human existence to the processes of the cosmos. The mechanics of supernovae also highlight the interplay between gravity, nuclear physics, and quantum mechanics. Electron degeneracy pressure resists collapse in the star's core until it is overwhelmed, while neutron degeneracy pressure halts the formation of matter for a brief moment, allowing the rebound to trigger the outward shockwave. Neutrino interactions, previously considered nearly invisible, suddenly dominate, transferring energy to the collapsing layers and aiding in their ejection. These subtle, quantum-scale interactions produce effects visible across light years, illustrating the universe's capacity to amplify microscopic processes into cosmic events. Beyond their chemical contributions, supernovae are also sources of energy and cosmic rays, seeding the galaxy with high-energy particles. These energetic particles influence the chemistry of interstellar clouds, trigger further nuclear reactions, and may even play a role in the formation of complex organic molecules, linking stellar explosions to the origins of life itself. In this sense, supernovae are not only forges of elements, but catalysts for cosmic chemistry on a galactic scale. The timing of a supernova is also critical. Massive stars burn through their fuel rapidly, living millions instead of billions of years. This accelerated timeline ensures that the universe's chemical evolution proceeds quickly, producing heavy elements early enough to seed future generations of stars and planets. Without the early deaths of massive stars, the cosmos would remain simple, dominated by hydrogen and helium, lacking the complexity needed for planets and life. Humanity's understanding of supernovae has deepened over centuries. Early astronomers observed new stars appearing in the night sky, unaware of the violent processes unfolding. Modern telescopes and satellites allow us to measure spectra, map shock waves, and detect neutrinos from these events, revealing the inner workings of dying stars. These observations confirm that supernovae are essential to the universe's chemical evolution, acting as both endpoints and beginnings, destroying stars while creating the elements needed for life. In essence, supernovae are the climactic finale of a massive star's life, yet they are also a prologue for the universe. The elements forged and scattered in these explosions are incorporated into new stars, planets, and eventually living organisms. Every gold ring, every piece of iron, every calcium atom in bones is a relic of these cosmic deaths. Supernovae are the universe's grand alchemy, converting stellar interiors into the building blocks of worlds and life, linking human existence to the death throes of ancient stars. Through supernova explosions, we see the universe as both destroyer and creator. The iron core, the accumulated fusion products, and the energy released in collapse converge to produce one of the most magnificent spectacles imaginable. These events highlight the cycle of matter and energy, illustrating how stars live, die, and give birth to the next generation of celestial structures. The cosmos, in this view, is a continuous cycle of creation and destruction, each stage feeding into the next, building the diversity of elements that populate galaxies and, ultimately, our own world. The study of supernovae also informs us about the origins of rare and precious elements. The gold in jewelry, platinum in technology, uranium for energy, and other heavy elements exist because massive stars lived, burned, and died in violent brilliance. Supernovae ensure that these elements are distributed across galaxies, becoming part of planets, life, and even human culture. Every piece of matter in our lives carries the legacy of these cataclysmic events, connecting us to the life cycles of stars that ended long before Earth formed. In contemplating supernovae, we realize that stellar death is not finality, but transformation. The star that collapses and explodes becomes the source of matter for new generations, continuing the cycle of cosmic alchemy. Iron, carbon, oxygen, gold, and every other element produced in these explosions are scattered across space, forming the raw materials of planets and life. The universe, through supernovae, is constantly renewing itself, creating complexity from destruction and providing the ingredients for existence as we know it. The supernova is therefore both an ending and a beginning. It concludes the life of a massive star, yet it seeds the cosmos with elements that will persist for billions of years. These explosions are a reminder of the intimate connection between destruction and creation, showing that death in the universe is never absolute but transformative. In witnessing or studying a supernova, we see the universe actively forging its chemical future, producing the diversity of elements that make life, planets, and stars possible. Through these violent, brilliant events, stars complete their role as cosmic forges. The products of their final fusion, scattered across the galaxy, ensure that future generations of stars, planets, and life have the ingredients necessary to exist. Supernovae are, in every sense, both endings and beginnings, a testament to the relentless creativity of the cosmos. They illustrate that from the limits of fusion and the collapse of a core, new possibilities emerge, linking the death of one star to the birth of new worlds and new life. Stellar winds and planetary nebulae. Not all stars end in dramatic supernova explosions. Smaller stars, those with masses comparable to or slightly larger than our Sun, follow a gentler yet equally profound path. As these stars age, hydrogen fusion in their cores diminishes, and helium begins to accumulate. The core contracts and heats, while the outer layers expand. The star becomes a red giant, a luminous and bloated version of itself, radiating energy across vast distances. During this stage, the star begins to shed its outer layers in a process driven by stellar winds, a steady outflow of gas and dust that carries newly formed elements into the surrounding interstellar medium. Stellar winds are subtle compared to supernovae, but they are far from insignificant. Over thousands or millions of years, the star loses a significant fraction of its mass, enriching the surrounding space with carbon, nitrogen, oxygen, and other elements synthesized during its life. These winds shape the star's environment, interacting with surrounding gas and dust, sculpting intricate structures, and contributing to the chemical complexity of the galaxy. The process is gradual, almost meditative, a quiet exhalation of matter that seeds future generations of stars and planets. As the outer layers drift away, the core of the star becomes exposed, revealing a dense, hot remnant composed primarily of carbon and oxygen. This remnant is known as a white dwarf, a stellar corpse that no longer undergoes fusion but continues to glow from residual heat. The exposed core radiates intense ultraviolet light, illuminating the gas and dust expelled earlier. The result is a planetary nebula, a colorful and ethereal shell of ionized gas expanding into space. The term planetary is a historical artifact, originating from early telescopic observations in which these nebulae appeared as small, round disks resembling planets. Planetary nebulae are both beautiful and scientifically significant. The expelled material contains the elements created during the star's lifetime, including carbon, nitrogen, and oxygen. These elements, now part of the interstellar medium, will eventually be incorporated into new stars, planets, and possibly life. The nebula acts as both a memorial to the star's life and a gift to the cosmos, ensuring that the matter created in the stellar core continues its journey through the universe. The structure of a planetary nebula can be remarkably intricate. Interactions between stellar winds, magnetic fields, and rotation create patterns ranging from simple spherical shells to complex bipolar structures. Knots of dense gas, filaments, and arcs may form, each reflecting subtle variations in the star's mass loss, internal dynamics, and surrounding environment. Observing these structures reveals not only the star's final stages, but also the interplay between stellar processes and the broader interstellar medium. The process of mass loss and planetary nebula formation is closely tied to stellar pulsations. Red giants often exhibit rhythmic expansions and contractions, driven by variations in core temperature and pressure. These pulsations help propel material outward, augmenting the effect of stellar winds and contributing to the nebula's shape. Dust forms in the cooler regions of the expanded outer layers, facilitating the transfer of momentum from radiation pressure to the gas. Over time, these mechanisms combine to peel away the star's envelope, layer by layer, until only the dense core remains. Stellar winds and planetary nebulae are essential to the cosmic cycle of matter. They provide a steady, predictable enrichment of the interstellar medium, complementing the more violent contributions of supernovae. Elements necessary for the formation of planets and life, particularly carbon and oxygen, are distributed gradually, allowing molecular clouds to incorporate them into future star systems. In this way, even stars that do not explode dramatically contribute profoundly to the chemical evolution of galaxies. The white dwarf left behind is itself a remarkable object. With a mass comparable to the Sun compressed into a volume similar to Earth, it represents matter in an extreme state. The electrons within the white dwarf provide degeneracy pressure, a quantum mechanical effect that supports the star against further collapse. These remnants will cool slowly over billions of years, radiating heat into space, sometimes forming spectacular binary systems where they may accrete matter from a companion star, potentially triggering nova eruptions, or even Type 1a supernovae under the right conditions. The nebula, glowing and expanding, becomes a living testament to the star's history. Ultraviolet radiation from the exposed core excites atoms in the surrounding gas, causing them to emit light at characteristic wavelengths. Oxygen glows green, hydrogen appears red, and nitrogen shines in deep reds and oranges. These colors, captured in telescopic images, reveal the chemical composition of the expelled material and provide a visual record of the elements that will seed future generations of stars and planets. The scale of planetary nebulae is immense, often spanning several light years across. They expand into the surrounding interstellar medium, interacting with gas clouds, magnetic fields, and previously ejected material. Over tens of thousands of years, the nebula disperses, blending with the cosmic environment. Yet even as the nebula fades, its contribution endures. The elements it carries are incorporated into new stars, planets, and potentially life-bearing worlds. In considering the process of stellar winds and planetary nebula formation, we recognize the universality of stellar influence. All stars, regardless of mass, interact with their surroundings, shaping the cosmos and redistributing the matter they have forged. Even stars like the Sun, whose deaths will be comparatively gentle, play a critical role in enriching the galaxy with carbon, oxygen, and other essential elements. The quiet exhalations of red giants complement the dramatic contributions of supernovae, together ensuring that the universe is chemically rich and capable of producing the planets, atmospheres, and molecules necessary for life. From a human perspective, this process is intimate and deeply connecting. The carbon in our cells, the oxygen we breathe, and the nitrogen in our atmosphere all originated in stars that passed through their red giant and planetary nebula phases long before the solar system formed. We are, in a very literal sense, products of stellar winds, cosmic dust, and the gentle dispersal of matter from dying stars. Our existence is a continuation of the life cycles of countless suns, a testament to the ongoing alchemy of the cosmos. Stellar winds and planetary nebulae also illustrate the balance between creation and destruction. While the star loses its outer layers, the energy and elements it contributes ensure that new stars and planets can form. The act of shedding matter is both an ending for the star and a beginning for the universe. In this sense, every death is a gift, every loss a seed for future creation, echoing the cycles observed throughout the cosmos, from the largest galaxies to the smallest particles. Furthermore, planetary nebulae are laboratories for astronomers. By analyzing their light spectra, scientists determine the abundances of carbon, oxygen, nitrogen, and other elements. These observations inform our understanding of stellar evolution, galactic chemical enrichment, and the processes that produce the elements essential for life. Planetary nebulae, though ephemeral on cosmic timescales, leave lasting imprints that guide our comprehension of the universe. The study of these nebulae also highlights the elegance of stellar evolution. The transition from red giant to white dwarf, accompanied by the ejection of enriched outer layers, is a carefully orchestrated process. Stellar pulsations, radiation pressure, and convection all collaborate to strip the star's envelope while preserving its dense core. The result is a combination of beauty, complexity, and function, a visually stunning nebula that is chemically significant, contributing to the ongoing cycle of matter in the galaxy. Ultimately, stellar winds and planetary nebulae are part of the cosmic narrative of recycling and regeneration. Stars forge elements in their cores, release them into the cosmos through winds and nebulae, and ensure that these elements are available for future generations. The matter that once formed the sun's core, or the outer layers of a red giant, continues to traverse space, eventually coalescing into new stars, planets, and perhaps life itself. In this way, the quiet deaths of smaller stars are as vital as the explosive deaths of massive stars, contributing to the chemical and physical richness of the universe. Through these processes, we see the continuity of matter and energy. Stars, whether massive or medium-sized, live, fuse, shed, and die, leaving behind elements that persist across eons. The carbon, oxygen, and nitrogen ejected in planetary nebulae become the foundation for future star systems. Every solar system, every planet, and every potential cradle for life is built upon the recycled material of these ancient stars. This is the cosmic cycle, ongoing and inexorable, linking past, present, and future across billions of years. In contemplating the significance of stellar winds and planetary nebulae, we are reminded of our own cosmic origins. The atoms in our bodies were forged not only in the hearts of massive stars, but also in the gentle, persistent processes of stars like the sun. We are children of the cosmos, inheritors of a chemical legacy shaped over billions of years by nuclear fusion, stellar winds, and nebulae. The quiet exhalations of dying stars have seeded the universe with the elements necessary for our existence. The ongoing dance of creation and dispersal continues. Planetary nebulae, despite their transient nature, ensure that matter flows from one generation of stars to the next. They are visible reminders of the universe's cycle of death and renewal, illustrating that even the most subtle stellar processes play a profound role in shaping the cosmos. Stars are not merely distant lights in the sky. They are forges, architects, and gardeners, creating, sustaining, and distributing the chemical building blocks of life. Through the study and observation of stellar winds and planetary nebulae, we gain insight into the complex processes that underlie the formation of elements and the evolution of galaxies. These stars, though no longer capable of the dramatic supernova of their massive cousins, contribute steadily and profoundly to the universe's chemical richness. Their matter becomes the raw material for planets, for new stars, and potentially for life. In this way, the universe continually recycles itself, a vast system of creation and transformation that stretches across space and time. In essence, stellar winds and planetary nebulae illustrate that the life cycles of stars are not isolated events but ongoing contributions to the cosmos. Each star, through its birth, life, and quiet death, participates in the universe's grand alchemy. By shedding their outer layers, stars ensure that the matter they have forged continues its journey, ready to be incorporated into new generations of celestial bodies. The universe is both a laboratory and a canvas, and the processes within stars are the brushstrokes and experiments that create its complexity and beauty. Cosmic recycling, stars, and the interstellar medium. The universe is a master recycler. Every star that lives and dies participates in an ongoing cycle, returning the elements it has forged back to the cosmos, enriching the interstellar medium, and providing the raw material for new stars, planets, and ultimately life. This process of cosmic recycling is both ancient and relentless, stretching across billions of years and spanning the vast expanses of galaxies. It is the mechanism by which the universe builds complexity, transforming simple hydrogen and helium into the rich chemical diversity that forms worlds like our own. At the heart of this recycling is the interstellar medium, ISM, a tenuous mixture of gas, dust, and plasma that permeates galaxies. Although the ISM may appear empty to the naked eye, it is in fact the repository of the universe's building blocks. It contains hydrogen, helium, and trace amounts of heavier elements, carbon, oxygen, nitrogen, iron, released by dying stars through supernovae, stellar winds, and planetary nebulae. These elements are mixed, stirred, and enriched over millions of years, creating the chemical canvas from which new stars and planetary systems will emerge. The journey of matter through the ISM begins with the death of a star. When a massive star explodes as a supernova, it hurls layers of newly forged elements into space at velocities of thousands of kilometers per second. These shock waves compress and heat the surrounding gas, creating turbulence that triggers the formation of dense clouds. Within these clouds, gravity begins to pull gas and dust together, initiating the collapse that will eventually give birth to new stars. The supernova not only disperses matter, but also acts as a catalyst, stimulating the next generation of stellar creation. Even smaller stars contribute to this cycle, albeit more gently. Through stellar winds and planetary nebulae, medium-sized stars release carbon, nitrogen, and oxygen into the ISM. Over millions of years, this material blends with existing gas clouds, gradually increasing their chemical richness. The ISM, therefore, is a cumulative repository of stellar history, a memory of countless generations of stars that have lived and died. Each cloud of gas and dust contains the legacy of billions of years of cosmic alchemy. The ISM is far from homogeneous. It contains regions of varying density, temperature, and composition, shaped by the energy and matter injected by stars. Hot, ionized regions, known as H2 regions, are illuminated by the ultraviolet radiation of young, massive stars, while cooler, dense molecular clouds harbor the potential for future star formation. Dust grains within the ISM act as catalysts for chemical reactions, allowing molecules such as water, carbon monoxide, and complex organic compounds to form. These molecules are essential ingredients for planets and potentially life. The enrichment of the ISM is a gradual, continuous process. As generations of stars live and die, heavier elements accumulate, allowing subsequent stars and planetary systems to be chemically richer than their predecessors. This is why later generations of stars, including our Sun, contain elements like carbon, oxygen, and iron, which were absent in the earliest stars formed shortly after the Big Bang. Cosmic recycling ensures that each generation of stars inherits the chemical legacy of those that came before, gradually building a universe capable of supporting planets, atmospheres, and life. The formation of new stars from the enriched ISM is itself a dynamic process. Within molecular clouds, regions of higher density collapse under gravity, forming protostars. As the protostar accretes mass, the surrounding material forms a rotating disk, known as a protoplanetary disk, from which planets, asteroids, and comets will eventually form. The elements released by previous generations of stars become part of these new systems, incorporating into planetary cores, atmospheres, and even organic molecules. In this way, the cosmic cycle continues, connecting the death of one star to the birth of another, and ultimately to the formation of planets capable of sustaining life. Supernovae and stellar winds also inject energy into the ISM, maintaining a delicate balance between turbulence and collapse. Shockwaves from supernovae compress gas in some regions while dispersing it in others, preventing runaway collapse and regulating star formation across galaxies. This interplay between energy, matter, and gravity ensures that star formation proceeds at a steady, sustainable rate, preserving the structure and dynamics of the galaxy while maintaining the cycle of chemical enrichment. The chemical evolution of galaxies is therefore intimately tied to cosmic recycling. Early galaxies, composed mostly of hydrogen and helium, lacked the heavier elements necessary for planet formation. Only after multiple generations of stars had lived and died did galaxies become chemically diverse, producing stars and planets with the rich variety of elements observed today. Carbon, oxygen, nitrogen, iron, silicon, and all the elements essential for life are the products of this ongoing stellar cycle, continually replenished and redistributed by cosmic processes. The ISM also serves as a laboratory for understanding stellar evolution and nucleosynthesis. By analyzing the composition of gas clouds, astronomers can trace the history of element formation, identifying the contributions of different types of stars. Observations of supernova remnants, planetary nebulae, and molecular clouds reveal the complex interplay between stellar death and cosmic creation. These insights allow us to reconstruct the chemical evolution of galaxies, understand the origins of elements, and appreciate the profound interconnectedness of the cosmos. Cosmic recycling also links directly to the origins of life. The elements produced and distributed by stars eventually form planets, atmospheres, and oceans. Carbon, oxygen, nitrogen, phosphorus, and other essential elements become part of the chemical inventory of planets. Water, organic molecules, and minerals, all necessary for life as we know it, are forged in the hearts of stars and distributed by supernovae and stellar winds. The universe, through this cycle of birth, death, and enrichment, creates the conditions necessary for life to emerge. From a human perspective, cosmic recycling is deeply personal. Every atom in our bodies has a history that extends back to previous generations of stars. The carbon in our cells, the oxygen we breathe, the the calcium in our bones, all originated in stars that lived and died long before the solar system formed. Our existence is directly tied to the processes of stellar nucleosynthesis and cosmic recycling. In this sense, we are not separate from the universe. We are a continuation of its ongoing cycles, inheritors of the elements produced and distributed by countless stars. The cycle of cosmic recycling also highlights the temporal scale of the universe. The processes of star formation, evolution, death, and enrichment occur over millions and billions of years. The material expelled by one generation of stars may take millions of years to coalesce into new stars and planetary systems. The universe is vast and patient, operating on timescales far beyond human comprehension. Yet despite the enormity of time and space, the processes of recycling ensure continuity, linking generations of stars and planets across epochs. In summary, cosmic recycling is the mechanism by which stars enrich the interstellar medium with the elements necessary for the formation of new stars, planets, and life. Supernovae, stellar winds, and planetary nebulae contribute to this ongoing cycle, distributing carbon, oxygen, nitrogen, iron, and other essential elements across space. Molecular clouds, enriched by previous generations of stars, collapse to form new stellar systems, continuing the cycle of creation. Through these processes, the universe builds complexity, diversity, and the potential for life. By understanding cosmic recycling, we grasp the continuity of matter and energy in the universe. The stars that have lived and died are not lost. They are contributors to the future, shaping galaxies, planetary systems, and the conditions for life. The universe is a continuous cycle of creation and transformation, with stars acting as both forges and distributors of matter. The chemical richness of galaxies, the formation of planets, and the emergence of life are all products of this ongoing cosmic alchemy. In contemplating the interstellar medium and the cycle of recycling, we also recognize the universality of physics. The same forces, gravity, nuclear reactions, radiation, and quantum mechanics, that govern stellar interiors also shape the distribution of matter in galaxies. Cosmic recycling is a manifestation of these laws on the grandest scales, ensuring that matter is conserved, transformed, and reincorporated into successive generations of stars and planets. Ultimately, cosmic recycling demonstrates the interconnectedness of the universe. The death of one star becomes the foundation for the birth of another. Elements forged in ancient stars become part of new planetary systems. Life, including human life, is a product of this continuous cycle. The universe is not static. It is alive with the movement of matter, energy, and elements, endlessly recycling itself across space and time. The study of cosmic recycling reminds us that we are part of a vast, ongoing story. The atoms in our bodies, the molecules in our environment, and the planets we inhabit are the results of billions of years of stellar evolution, death, and dispersal. We carry within us the legacy of countless stars, each contributing to the complex chemical and physical tapestry of the cosmos. In this way, cosmic recycling is both a scientific process and a deeply human story, connecting us to the universe and to the stars that shaped it, our cosmic connection. When we look up at the night sky, it is easy to feel small and insignificant. The stars shimmer, distant and untouchable, and the vast stretches of space seem to dwarf our everyday concerns. Yet the truth is far more intimate. We are not merely observers of the cosmos, we are participants. Every atom in our bodies, every molecule in the air we breathe, Every trace of matter around us is the product of countless stars that lived, fused, and died long before the Earth formed. The universe, in a profound and literal sense, resides within us. The carbon in our cells, the oxygen we inhale, and the iron in our blood all have origins in the hearts of stars. Some of these stars were massive and short-lived, ending their lives in cataclysmic supernovae, scattering their enriched guts across space. Others were smaller, like our Sun, whose gentle stellar winds and eventual planetary nebulae contributed carbon, oxygen, and nitrogen to the interstellar medium. Over millions and billions of years, this enriched material coalesced into new molecular clouds, giving rise to our solar system. When we contemplate this, we realize that life itself is a continuation of the universe's cycles of creation and transformation. Our connection to the cosmos is therefore not metaphorical, it is literal. The elements that sustain life were forged in the nuclear furnaces of stars. Helium fusion produced carbon and oxygen. Advanced fusion in massive stars generated neon, magnesium, and silicon. Supernova explosions forged iron and heavier elements. Planetary nebulae contributed nitrogen and carbon to the interstellar medium. Every stage of stellar evolution contributed to the chemical environment that made Earth habitable. In a very real sense, we are made of star stuff. The process that connected ancient stars to life on Earth is both intricate and awe-inspiring. Consider oxygen, formed in the cores of massive stars through helium and carbon fusion. It was later dispersed by supernova explosions and stellar winds. Over time, this oxygen mixed with hydrogen in interstellar clouds, eventually becoming part of water molecules on the forming Earth. Carbon, nitrogen, and other essential elements followed similar paths, incorporated into planets, atmosphere, and eventually the biochemistry of living organisms. Without these stars and their complex life cycles, the conditions necessary for life would never have emerged. The cosmic connection extends beyond mere chemistry. It also shapes our understanding of time and existence. The stars whose material now resides in us existed billions of years before the Sun ignited. By studying their remnants in supernovae, planetary nebulae, and enriched interstellar clouds, we trace a lineage that predates our solar system, our planet, and our species. We are connected not only to the stars that still shine in the sky, but to generations of stars that have long since vanished. The universe is a continuous chain of matter and energy, linking the past to the present, the dead to the living, and the distant to the intimate. Even the metals in our technology, the gold in jewelry, the uranium used for energy, and the iron in construction all originated in stellar processes. Supernovae forged these heavy elements in moments of extreme temperature and pressure, ejecting them into the cosmos to eventually become part of planets and human civilization. Humanity's material culture is thus rooted in the chemistry of ancient stars, connecting us to the cosmos in ways that are often invisible but profoundly fundamental. Our cosmic connection is also philosophical. Understanding that we are made of star stuff fosters a sense of humility and wonder. The universe is not a distant, detached entity, but an intimate participant in our existence. Our bodies, our planet, and our society are products of billions of years of cosmic evolution. The stars that seem so far away are, in truth, our ancestors, our material progenitors. The vastness of space is not a barrier, but a bridge, linking us to processes that transcend human lifetimes, and even the lifespan of civilizations. This connection can also be experienced emotionally. Imagine tracing the path of an atom in your body. It might have formed in a supernova explosion, traveled through interstellar space for millions of years, been incorporated into a cloud that collapsed to form the solar system, and finally become part of the Earth and life itself. That atom could have once been part of a star's core, experiencing unimaginable pressures and temperatures, contributing to the star's radiant energy. Today, it resides in you, completing a journey that links cosmic events to human life in a tangible way. Moreover, our connection is ongoing. Stars continue to live, fuse, and die throughout the galaxy, continuously enriching the interstellar medium with new elements. Molecular clouds absorb this material, and new stars and planetary systems form. The same processes that contributed to the origin of life on Earth are still occurring in distant corners of the Milky Way. Somewhere, new planetary systems are forming, seeded with the elements created in previous generations of stars, continuing the cycle of cosmic creation. We are both descendants and witnesses to these processes, intimately tied to the universe's ongoing evolution. Observing our cosmic connection also illuminates our place in time. The atoms that constitute our bodies were forged in events that occurred billions of years ago, long before humans existed. Supernovae and planetary nebulae shaped the chemical landscape of the galaxy, setting the stage for the formation of the solar system. By understanding the life cycles of stars, we recognize that our existence is not isolated, but deeply embedded within the continuity of cosmic processes. Our lives are brief in comparison, yet they are part of a larger, ongoing story that spans the universe itself. This perspective also underscores the fragility and preciousness of life. The conditions required for life depend on a precise mix of elements and environmental stability, all of which are products of cosmic recycling. The carbon, oxygen, nitrogen, and other elements in our environment are finite resources, synthesized in stars and delivered through a delicate balance of processes. Recognizing our connection to these elements fosters an appreciation for the intricate interplay between stars, planets, and life, highlighting the interdependence of all cosmic processes. The human connection to the stars also extends to our quest for knowledge. Throughout history, humans have gazed at the night sky, striving to understand our origins and place in the universe. By studying stellar nucleosynthesis, supernovae, and cosmic recycling, we trace the lineage of matter from the hearts of ancient stars to the Earth and our own bodies. Astronomy and astrophysics allow us to comprehend our material and temporal connection to the cosmos, revealing that our existence is intimately tied to events that unfolded billions of years ago in distant galaxies. In addition, this connection fosters a sense of universality. Every human, every living organism, and every planet composed of elements forged in stars shares a common origin. Carbon-based life on Earth, the oxygen in our atmosphere, the iron in our blood, all are products of the same processes that govern stars across the universe. Recognizing this shared heritage transcends boundaries, cultures, and species, reminding us that life itself is a continuation of the universe's chemical and energetic cycles. Ultimately, our cosmic connection is a story of continuity, resilience, and wonder. From the hydrogen and helium created in the Big Bang, through the complex fusion processes in stars, to the dispersal of elements via supernovae and stellar winds, every stage has contributed to the chemical richness necessary for planets and life. Humanity's existence is not an isolated phenomenon, but a natural consequence of these processes. We are the culmination of billions of years of stellar evolution, intimately tied to the cosmos both materially and temporally. As we gaze at the stars tonight, we can recognize ourselves in them. The light we see may come from stars that have long since died, yet the elements they produced live on in the atoms that compose our bodies. The universe is not distant and indifferent. It is deeply entwined with us. In understanding the origin of elements and the life cycles of stars, we come to appreciate the profound truth. The cosmos is both our heritage and our home. Our connection to the stars also imparts responsibility. Recognizing that we are products of the universe's cycles of creation and destruction inspires awe and humility. It reminds us that life is part of a larger continuum, that our existence is intertwined with cosmic processes far beyond our lifetimes. Every breath, every heartbeat, every action is part of a universe that has been shaping and reshaping itself for billions of years. The story of the elements is, in essence, our story. Through this cosmic perspective, we see that life is not separate from the universe. It is an extension of it. The atoms in our bodies were forged in stars, recycled through generations of stellar deaths and planetary formation. Our existence is a testament to the enduring processes of cosmic creation and transformation. The human story, in every sense, is written in the language of stars. By embracing our cosmic connection, we gain not only knowledge but perspective, humility, and wonder. We see ourselves as participants in a vast, ongoing process of chemical and physical evolution, linked to stars that lived and died long before the Earth formed. Our bodies, our planet, and our lives are intricately connected to the universe's history, a continuous cycle of creation and transformation that extends across billions of years and countless light years of space. The eternal dance of creation. The universe is a rhythm of birth, life, death, and rebirth, a continuous, unending dance in which matter and energy flow, transform, and reassemble across the cosmos. Stars live, fuse, and die, releasing the elements they have forged into the interstellar medium. These elements, enriched and scattered across space, form the foundation for new stars, planets, and life. This cosmic cycle, spanning billions of years, is the eternal dance of creation, a process both violent and delicate, grand and intimate. Every star contributes to this ongoing rhythm. Massive stars, burning brightly and dying spectacularly in supernovae, scatter heavy elements like iron, gold, and uranium across the galaxy. Smaller stars, through planetary nebulae and stellar winds, gently enrich the cosmos with carbon, oxygen, and nitrogen. Each generation of stars inherits the chemical legacy of its predecessors, building complexity upon simplicity, creating the conditions necessary for planets, atmospheres, and ultimately, life. Consider the life cycle of a single massive star. It begins as a cloud of gas collapsing under gravity, igniting fusion in its core. Hydrogen becomes helium, helium becomes carbon and oxygen, and successive fusion shells produce neon, magnesium, silicon, and iron. When iron accumulates, fusion can no longer generate energy, and the core collapses, triggering a supernova explosion. The resulting shock waves disperse newly formed elements into space, where they mix with interstellar gas, eventually forming the next generation of stars and planetary systems. In this cycle, death and creation are inseparable, the ending of one star setting the stage for the birth of another. Even the gentler stars, like our Sun, participate in this dance. After billions of years, hydrogen in the core depletes, helium accumulates, and the star expands into a red giant. Through stellar winds and eventual planetary nebula ejection, carbon, oxygen, and nitrogen are returned to space. These elements mix into molecular clouds, seeding future stars and planets. The white dwarf that remains continues to glow for billions of years, a reminder that even in death, stars contribute to the cosmos. This ongoing cycle of creation ensures that the universe grows richer with every generation of stars. Early galaxies contained primarily hydrogen and helium, the products of the Big Bang. Only through successive generations of stellar evolution did the universe accumulate the heavier elements necessary for planets, complex chemistry, and life. Each generation of stars builds upon the previous one, enriching the interstellar medium with a more complex chemical palette. Without this process, the universe would remain simple and sterile, incapable of supporting the diversity we observe today. The eternal dance of creation is not only chemical, but energetic. Supernovae release vast amounts of energy, creating shock waves that compress gas and dust, triggering the formation of new stars. Stellar winds from red giants and massive stars stir the interstellar medium, shaping the density and structure of molecular clouds. Radiation from stars ionizes gas, carving bubbles and cavities in the surrounding environment. These energetic processes are intertwined with the flow of matter, demonstrating that creation in the universe is both dynamic and interactive. Every element forged in stars carries a story: carbon in our cells, oxygen in the atmosphere, iron in our blood, gold in jewelry, and uranium in the Earth's crust. All were created in the nuclear furnaces of stars and dispersed through cosmic recycling. These elements have traveled through interstellar space, become incorporated into new generations of stars and planets, and eventually found their way into life. In every sense, we are connected to this eternal dance. We are participants in the universe's ongoing cycle of creation, living embodiments of processes that began billions of years ago. The cycles of creation and destruction in the cosmos also highlight the universality of physical laws. Gravity shapes the collapse of gas clouds and the structure of stars. Nuclear physics governs fusion processes and element formation. Quantum mechanics determines the stability of atomic nuclei and the behavior of electrons in degenerate cores. Across vast distances and timescales, these fundamental laws orchestrate the cosmic dance, ensuring continuity, transformation, and complexity. The universe is both orderly and dynamic, a stage upon which creation unfolds with precision and spontaneity. Observing this process inspires awe. From the gentle glow of a red giant to the explosive brilliance of a supernova, from the quiet ejection of a planetary nebula to the subtle enrichment of molecular clouds, the cosmos is alive with cycles of transformation. Stars, through their lives and deaths, act as forges, alchemists, and gardeners, shaping the chemical and physical fabric of galaxies. Every planet, moon, and living organism is part of this continuous process, a testament to the interconnectedness of all things. The eternal dance of creation also carries profound philosophical implications. Understanding our connection to the universe reveals that life is not an isolated phenomenon, but a continuation of cosmic processes. Every breath, every heartbeat, and every action is linked to the flow of matter and energy across billions of years. The elements that sustain us were once part of stars that lived and died long before Earth formed. Recognizing this connection fosters humility, wonder, and a sense of belonging to something vast and enduring. Furthermore, this cosmic cycle demonstrates the resilience of matter and energy. Stars may die, but the elements they create persist, forming new stars and planets. Supernovae and stellar winds ensure that matter is continuously recycled, transformed and reintegrated into the cosmos. Life, planets, and galaxies are the products of billions of years of ongoing processes, a testament to the universe's capacity for renewal and creation. In this sense, death is never absolute. It is transformation, a necessary stage in the cycle of cosmic evolution. The dance of creation also reveals the scale and timescales of the universe. Stars form, evolve, and die over millions to billions of years. Supernova remnants expand across light years, enriching the interstellar medium slowly yet persistently. Molecular clouds collapse over millions of years to form new stars. This immense temporal scale provides perspective on our place in the universe. Our lives are fleeting, yet we are part of processes that span eons and shape the very structure of galaxies. Through cosmic recycling, the universe builds complexity incrementally. Simple hydrogen and helium from the Big Bang are transformed into carbon, oxygen, nitrogen, iron, and countless other elements through fusion and stellar death. These elements are distributed, mixed, and reassembled to form planets and the chemical environments necessary for life. The universe's evolution is a continuous accumulation of matter and energy, each cycle building upon the last, ensuring the emergence of complexity, diversity, and the potential for consciousness. The eternal dance of creation reminds us that the cosmos is not static, but dynamic. Stars, planets, and galaxies are in constant flux, matter and energy moving, interacting, and transforming. Every atom in existence has participated in this cycle, tracing its history through countless generations of stars. From the smallest grain of dust to the largest planet, every object in the universe is part of the ongoing flow of creation. In reflecting on this dance, we see our own lives as threads in the grand tapestry of the cosmos. Humanity, the Earth, and life itself are the products of billions of years of stellar evolution, cosmic recycling, and chemical enrichment. We are, in every sense, children of stars, inheritors of a legacy forged in the hearts of ancient suns. Every molecule in our bodies, every element on our planet, carries the imprint of this eternal process. The dance continues. New stars ignite in molecular clouds, fusing hydrogen into helium, producing carbon, oxygen, and heavier elements. Massive stars reach the end of their lives, exploding in supernovae that disperse these elements into space. Smaller stars shed their outer layers, forming planetary nebulae that gently enrich the interstellar medium. Matter and energy circulate, transform, and reassemble, a rhythm that has persisted for billions of years and will continue for billions more. In contemplating the eternal dance of creation, we gain both knowledge and perspective. We understand the origins of the elements, the life cycles of stars, and our place in the universe. We recognize the continuity of matter and energy, the resilience of creation, and the interconnectedness of all things. The cosmos is alive with cycles of birth, death, and rebirth, and we, as conscious participants, are witnesses to and products of this magnificent process. Every atom in our bodies, every grain of dust on Earth, every molecule in the air traces its lineage to this eternal cosmic dance. The stars that forged them lived and died long before our solar system existed, yet their influence continues, shaping the planets, life, and civilizations that now inhabit the galaxy. The universe is not distant or indifferent. It is intimately connected to us, and we are intimately connected to it. The eternal dance of creation is both a scientific truth and a poetic reality. It tells the story of matter cycling through generations of stars, of energy flowing across space, and of life emerging from the cosmic forge. It is the ultimate demonstration that creation is never-ending, that death leads to life, and that the universe, in all its vastness, is a tapestry of interconnected processes that continue to shape existence. In the final analysis, the eternal dance of creation is the story of the cosmos itself, a rhythm of stars igniting and dying, elements forming and dispersing, matter recycling and evolving, and life emerging in response. It is a story without end, a cycle without beginning, a dance that connects every particle, every star, and every living being. And as we contemplate this dance, we are reminded that we are both products and participants, forever entwined with the cosmos, forever part of the universe's magnificent, unending rhythm.